Okay, so first, a few announcements regarding this strike. Please follow the announcements on @stand. They can change. The situation is evolving, and we'll keep you informed to the best of our abilities. And as you saw the post most recently, we're not going to have tier office hours this week. So just to at least, I'm going to have extra office hours today and tomorrow from 2 to 6 and 2:30 to 6:30, especially given that we have an exam due on Wednesday, might be somewhat helpful. And exam 2 will be here in class and in the other room. I'll try and move around between the two places. I think we can manage that. And it covers lectures 9, 10, 11, 12, 13, 14. So 6 lectures. It includes reductions. A couple of you asked, everything and up to including lecture 14. So all the things on homework 4, for instance, will be part of the exam, could be part of the exam. And the logistics are the same as for exam 1. So no notes, no book, no cheat sheets. And instead, expect delays in grading for exam 3 and the homeworks are going forward, but we'll see how things develop. Okay. And as per our original plan, we didn't have a discussion section scheduled for this Friday, but instead, to make up for the fact that we're using a lecture for exam 2, we'll have a remote lecture on 11/18 from 2 to 3:50 p.m. Okay, in our usual Zoom link. Any questions about the exam or the logistics? No? All good? Okay. All right. So with that out of the way, so let me now talk about what we're going to talk about today. So first thing is, last class, we talked about many important results. So we saw that toddler is uncomputable. We saw that the halting problem was uncomputable. And then we introduced this notion of reductions and use them to show that halt on 0 is uncomputable.
You guys check on her.
And what I want to do today is kind of, first review a little bit of what we discussed in the last lecture. There were many questions on @stand about the reduction for halt on 0 in particular, and also why halt itself is uncomputable. So what I want to do today is do another example of a reduction, just so that the definition and its use is clear. And also kind of present a slightly different proof of halt that it is uncomputable. Okay, it's going to be slightly different in the sense that it's almost the same proof, just wrapped in different language. Okay. And then we'll talk about what our next topic would have been, which is whether or not we can verify software, right? What are the challenges in it and what can we do to mitigate them and so on. Okay. So okay, so recall. Right, so we define the halt function. And it said, if I give it the description of a machine and an input X, it should say 1 if M halts on X and 0 if not. Okay. This is how we define the halting problem. And we saw that halting is uncomputable by a reduction from toddler, right? So we showed that toddler was uncomputable, and then we showed how we could use halt to solve the toddler problem. But today, just to give you a better sense of what's the inherent difficulty in halting, let's do a different proof. Okay. Again, as I said, it's not like really different. It's just kind of cleaner, I think, if you are only interested in halting. Okay, so the idea here is similar to what we do for toddler, which is to kind of try and do the opposite of what the machine would do on itself. Okay, so yeah, let's say we cannot call it proof yet. Suppose there was a machine, let's call it H for halt. That computed halt. Okay, so we are going to try and get a contradiction to this, right? You know, that there is a machine H that computes halt, and we want to get a contradiction. Suppose there is such a machine. I'm going to define a new function which does the following. Okay, it's going to be called can't solve me. All right, and it takes the description of a machine as input. You know, whatever input you give as a binary string, it's going to interpret as the description of a Turing machine. Basically, you're giving it the source code of some program, and it's going to do something based on that, right? And I'm going to use Python notation, just clear. And what it does is it checks if the input machine halts when given itself as input. Okay, we can do this now because we have a machine H that computes halt. That's our assumption, right? That's a very strong assumption. As you'll see, it's not possible. But if you had that assumption, this is one of the things you can do. I can run H on m comma m, the description of the machine on itself. And if it equals 1, meaning H says, you know what, the machine M halts when given its own description as input. Okay, so then kind of I'm going to mimic the toddler behavior and try and do the opposite. So if it halts, I'm just going to do while true, just some dummy statement. So if H says M halts on itself, I'm going to go into a loop. Okay. Else, okay. So else means that, you know, you really had H of M comma M equals 0, right? All right. Any questions about the program? Okay. Again, all we're doing here is taking the description of the program for H and writing down a new program. We're not running anything. This is something to always keep in mind when you're doing these reductions, right? We are just trying to write down the source code of a new program. We're not executing the program, okay? This is where we view program as code, right? And that's an important distinction. That's what allows many of these impossibility results and other things to go through, okay? So this is a new program. Let's call it can't solve me. Okay, so far so good. You know, nothing seems mysterious, but where would the contradiction come from? Any guesses? Any suggestions? There should be something like, you know, very eerie about this definition. Think of what happened when we did toddler, right? So if we had a machine which computed the toddler, we asked a simple question. What does the toddler do when given itself as input, right? So any suggestions here? Like, you know, what would be, yeah?
We're checking the source clear at mhalts, but then we're like looking for with the dummy statement,
right? Right. So, you know, let's just ask a similar question as we did, which is, what does can solve me do if I give its own source code as input? Okay, the same sort of game we played with toddler, right? You know, that's how you defeat a toddler. You just mimic their own behavior. Okay, so let's do the same thing. You know, there are two cases. So it's a simple question. So what is this guy? equals dash. What is this going to be? What would can't solve me output on can't solve me? All right. So let's do case analysis. Okay, now if the two options, right, and it's either 0 or 1. If it is 0, then what? Okay, so if it is 0, meaning the program halted and gave some output. Okay. Right. So this implies that can solve me halted. Okay. Okay, so maybe it doesn't even have to be 0. So let's say it halts and gives some output. So if it halted, then what would happen? So remember, we're giving the same program as input, right? So h of can't solve me would be 1 because you halted. So you would end up in a loop. That means you did not halt. Doesn't pass, right? It doesn't make sense. Okay. Implies can't solve me halted. Implies we would enter the while loop. This run, right? Okay, so it implies we do not halt. Okay, which contradicts where we started out with. Okay, so that's the pathological behavior that we kind of saw it already in the toddler case, and this is another example of the same thing. Okay, any questions about this? Okay, so let's do the same thing again. There's another case, maybe does not halt. Okay, if we assume that it halted, we got a contradiction. But what happens if it does not halt? Well, if it does not halt, you would enter the else loop and you're halting. Okay, because you're doing the exact opposite. So implies we would enter the else condition, implies we would halt. Okay, so that's again a contradiction. So no matter what we do, we are ending up in this bizarre contradiction, right? Yeah.
I understand why. We're looking at the program, not looking at the input programming first.
Right, the whole program. Right, so but the whole program is being given as input to the whole program. Right, so there's here we're running M on M. That's one level of description, using the program and itself again, right? But then we're also looking at what happens if I do can solve me on can solve me. Okay, so when it enters here, it's asking, does can solve me halt on can solve me? If it won, you go here, otherwise you go here. Okay, so there's two levels of the self-reference which we are exploiting. Thank you. Yeah, which if or else we are going here. Yeah, exactly. Okay. Any other questions about this? I would say, this is the same thing that happened in toddler and the earlier reduction. There, we kind of pinpointed it more to, okay, you can't have x equals not x. Okay. Here is kind of you're entering the loop. If you're not supposed to. If you're not supposed to enter a loop, then you are entering the loop. Okay. So we are getting a contradiction no matter what we do. There's a question, if we switch the while loop and the return statement, this would become computable, right? Yeah, it would become computable, but so that's just like some computable program, so it wouldn't give us a contradiction, but that doesn't mean there is no other contradiction, right? So we're trying to investigate all implications of assuming that there is a machine H that computes halt. Okay. So yeah, that's a good question. Like the question was, what if I switch these two cases? Then you would not get a contradiction, but that doesn't mean there isn't one. Okay. All right. So this implies that no matter what, we are getting a contradiction. Implies halt must be uncomputable. Okay. There's also actually a fun sort of animated video of this proof. It's a bit cheesy, so I'm not going to play it here, but you're welcome to watch it. I'll put a link on YouTube. A small bug. That's another reason I'm not playing it, but it's okay. Okay, but I'll put a link to it. I think it's a good illustration of what's going on in the proof. Yeah. We have to do two cases, right? It could be that, in some case, you might end up in a good scenario. In another case, you might not end up in a good scenario. So we're ruling out all possibilities. Like, it's not that it doesn't halt, it doesn't halt. In all of these cases, we are ending up in a contradiction. Okay. Any other questions? Yeah. Right. So it is a contract example, but we are getting a contradiction starting from this assumption, right? So the only thing that we assumed in this is that there exists an edge. Okay, that's the central piece of this whole puzzle. That if I assume I can decide halting, then I can do all of these negations. Okay, so it's the only assumption that's going into this contradiction. So the assumption must be false. Okay. All right. Any other questions? Okay, let's do one more example of a reduction, and then we'll move on to the next topic. So I'll call this example. Okay, not okay. So another example of a reduction. Okay, so I'll call this function not empty. Okay, and once again, it's a function which views its input as descriptions of Turing machines. It's going to view its input as source code of some program. And it checks if there is some input which makes the machine or program output 1. You give it some program. If there is something which makes it output 1, it has to say yes. There is something which could make it output 1. Otherwise, it says 0. Okay. So that's a very simple, seemingly simple definition of a function. Given a program, is there something which makes it output 1? Is there some input that can make the program output 1? All right. So there's a question, could we cite the can-solve me function as a proof that a halt function can certainly never be computed? Or can we only say that we do not yet know how to compute it? It's the former. The proof says that there is no way you can compute halting, no matter how much power you have or what model you will have based on the church-turing thesis. Okay, and I would say, it's even worse than that. If someone gives you a program and says, someone is selling you software to say, okay, here's a program, it costs $1,000 and it will solve halting problem. You can take exactly this can-solve me routine, feed it into it, and make it fail. It's like a bulletproof test case on which someone gives a machine claiming to solve halting, it will fail. Okay. All right. Okay, so coming back. So for instance, if I have, let's say my program is def dummy1 OZ says return 0. Okay. So what is not empty of dummy1? It would be 0, right? Because on every input, it's just outputting 0. So it would only give this. Maybe what if I have, maybe, let's say, okay, so let's say this is another program. So what is not empty of dummy2? It's going to be 1, right? Because there is some input on which the program outputs 1. Okay. Most inputs is giving 0, but there's something, and that's all that matters for the definition of not empty. Okay. So now, we want to build, or we want to check if there is a program which can take source code like this and tell me something about its input output behavior, right? Is it possible or is it not? And my claim is that it's not possible. And why? I can prove it with a reduction from halt on 0. Okay. So we'll prove it by a reduction from halt on 0. All right. And when, often if you have to use the reduction, the first piece of the puzzle, I would say, is to pick the right starting problem to reduce from. Sometimes it's better to use halt on 0. Maybe sometimes it's better to use halt and homework for, and there's a couple of practice problems within the homework as well, which kind of give you different things to try out when you have to use reductions. Okay. Halt on 0 is particularly useful because it's kind of simple enough, which makes it amenable for many kinds of reductions. Okay. So any suggestions on how I can reduce halt on 0 to not empty, right? So what do I mean? So here are the inputs for halt on 0. And here are the inputs for not empty. They're kind of living in the same space, but that's fine. And we want a reduction R, right? Such that halt on 0 on any input M would exactly equal not empty of R. Right? So I give you the source code of some program, transform it, give me a new source code so that this equality holds. Right? And any suggestions and what it might be? There are many options we can pick, but tell me one thing. Yeah. Maybe, but I think it can be even simpler. Let's see. Yeah.
It'd be a program that just takes any input and then runs eval on and then returns.
Yeah, that would work. I mean, that's I think watcher size would also work, but maybe this is simpler. Okay, so you could just say, I'm going to take so remember, when we're designing the reduction, the new program already has access to the source code for M, right? So that's why we are able to do something like this eval of M, because we already have M. Okay, and the suggestion was, just run M on 0 using eval, and then you return 1. Okay, so this is R of M. It's a new program. Okay, and again, I keep emphasizing this. R is not running any programs. It's just transforming the source code. Okay, so this is the program N. Okay. So now we have the reduction, it is efficient, it is computable, because all we are doing is kind of just adding a couple of lines, run eval, eval is computable, and then you have return statement. Okay, that's the only thing that we're doing. And let's check why this is a valid reduction, right? So why is this valid? Meaning we have to check why it satisfies this equation, if at all. Okay, and you can pretty much always check it by case analysis, right? So let's do a case analysis. Okay, case 1, if halt on 0 of M equals 1, meaning the input program M does in fact halt on 0, right? So what can you tell me about not empty of N in this case? Okay, is there any input on which N would output 1? Yes, in fact, on all inputs it would output 1, because it would halt here and then move on to the next step and it would say return 1. Okay, so it would be 1 on all inputs Z, N of Z would equal 1. So in particular, there is at least one input on which this happens. Okay. Case 2. Well, if halt on 0 of M equals 0. What happens in this case? Equals 0 means M is not halting on 0. So in this case, N never returns any output on any string. It's just going to end up in a loop, because M is ending up in a loop. N is going to end up in a loop. So it's never halting. So there is no output. So in particular, there is no string which makes it output 1. So implies not empty of M equals 0. Okay, because on all inputs Z, N does not halt. All right, So we have verified that the equation that is essential for the reduction to work is correct. Okay, so this equation holds. So we have a reduction from Halton 0 to not empty. Yeah. So, I mean, doing the two cases is kind of, so what you're asking for is, if not empty was 1, you should check this is 1, okay? But this is kind of equivalent. Like, whether A implies B, and then you check not A implies not B, that's the same as checking the converse. Okay, that's another way to do it, but this is often easier, at least for the case of reduction that we are looking at. Okay, yeah. Sorry, say that again. This is a car production. So, I mean, basically car reductions, I would say, are kind of simpler reductions. So for the most part, most of the things that we look at are car reductions that kind of simplify the search space of reductions. Because, if you ask you to reduce problem A to problem B, there are like so many choices, right? And, some problems you can't just do a car reduction. You have to do something on top of that. But at least for many of these examples, car reductions themselves suffice. So car reduction is kind of restrictive because you do this transformation and like you call this black box, someone gave you for not empty only once, right? It's like saying, okay, there is this oracular black box, but you only get one shot at using it. And you still use that to solve your original problem. Whereas technically, even if you could use it multiple times and solve it, you might get a contradiction to uncomputability. And that's the Turing reduction part. Okay. So there's a question, how do you know what to define N as? Yeah, so that's kind of where you have to be mindful of the definition of the problem and play around with a few examples and kind of develop some sense of how to come up with these reductions, right? As I said, to come up with a reduction, you have to first choose the right problem to reduce from. And if I say, okay, show that this problem is uncomputable or something like that, you have to pick the right starting problem to reduce from. And then you have to play around with it to make sure you satisfy this equality. Okay, so often, it's if you start with the right problem, sometimes it becomes easy enough, but it involves some trial and error and kind of playing around with the definitions of the two problems. Okay. Any other questions? And if you've seen reduction, I mean, if you've done CS 180, there are also reductions that show up there, right? And the NP completeness and so on. It's kind of similar, but here they're, I would say, simpler than the reductions you might have seen in CS 180. Yeah?
Just to clarify, M does not fall from 0 in the function and will never reach the return point.
Right, yeah. So that's exactly why there's no input on which you're even returning a value, let alone returning 1. Exactly. Yeah. Yeah, so I mean, I'm basically inserting if and only if, and doing two implications, right? So we have to check basically equals 1 if and only if this guy is 1. So one way to check it, if it's 1, this is 1. If this is 0, this is 0. So both are equivalent. It is unidirectional, but I'm doing like 2 cases. Okay, so I mean, as an aside, if I want to show A is if and only if B, let's say A and B are 2 logical statements, then I have to show A implies B, okay, and not A implies not B. Okay, so this is equivalent to saying B implies A. Okay, but better to think of it just as a case analysis, right? You have this equality, the 2 cases for the left-hand side, it's 1, the right-hand side is also 1, the left-hand side is 0, the right-hand side is also 0, so both are equal. Okay, yeah? So the reduction is only returning this thing, and the program is actually returning the numerical value 1. No. So the reduction is returning this description, but n itself, the source code, has a specific return value. Okay. All right. Any other questions? Okay. So if there are no other questions, let me now move to the next topic that is very important in many different areas of computer science. And the reason it's, as you'll see, there are whole new areas built on this is because of what we're going to do next. Okay. And like a one-word summary of this is, you can say, software verification. Okay. So what does software verification broadly mean? So it means something like this. Now, someone gave you have some functionality, right? And you hire some software engineers. Okay, code this up. Hire some undergrads. You have a startup. Code this up. But then the question is whether you trust the code directly, or you want to verify that the code does satisfy what you wanted it to do. Okay. So one very concrete way to formalize, or very concrete example of such a scenario is something like this. Okay. Suppose I have two programs, program A and program B. And this maybe many lines here, right? Whatever. Programs are, again, you can think of them as Turing machines, but really just think of any high-level programming language. And I ask you the question, are these two equivalent? Meaning, are they performing? Do they have the same input-output behavior? Like, for instance, let's say I have one program which says, okay, maybe it's def, let's say, we are only going to do this for positive numbers. Okay, so this is program number one. The other program is does the same thing at the beginning. It does a simple case check. And then I have two programs, and you can kind of check manually just by looking at it that they're doing the exact same thing. They just double the number if the number is greater than or equal to 0, and otherwise they return 0. Like really silly programs, but they both have the same exact functionality. Okay. And the main thing within software verification is to check whether two programs are equal, or one of the goals is that you want to check if two programs are equal, and you want to do this not manually, but use this automatizable. So we want to reason about programs. So can we reason about what programs compute? Okay, like for instance, does the program code compute what I wanted it. So imagine, you know, you are writing a program for multiplication, and you're going to put this on some chip, which on some computer, which is then, you know, being sent to Mars, right? So if your multiplication algorithm implementation is wrong, it will be a total disaster, right? You want to be absolutely certain that this is correct. How can you do that short of basically enumerating all possible inputs and checking if you're computing the right answer? Can you do this in some mechanical way, or even better, by writing a program itself? Okay, another version of the same thing is I give you two programs. Are they computing the same thing, right? And this example of multiplication on a chip, that's not really just a theoretical scenario. There was, a long time ago, Intel designed a chip that was supposed to do division pretty well. And they found a bug by using some automated software verification tools. And then they had to recall, do a lot of things. It cost them a lot of money. But they did find the bug using automated software verification tools. Okay. But that was like, you know, for some very simple algorithm with very small input sizes, but even then it was challenging. But now we're asking, can I do this? Can I ask this question in a meaningful way? And are there interesting scenarios where I can answer it? And if you can do this, then the applications would be amazing, right? You know, you can really get rid of software testing. Right? It would also be very useful in computer security. Right? You know, sometimes you get a program which claims to be doing something, but then there's some hidden code in there which is not doing what you wanted it to. But if you can check if the programs are equal, and maybe you can just detect any such bugs or malicious code. Okay, you can also, in compilers or programming languages, would be an amazing tool to have. Right? If you could reason about programs, maybe not like, you know, very, very complicated questions, but at least two of these natural ones, like, does it compute the function that I wanted to? Or, you know, give you two programs, are they doing the same thing as each other? Okay, just doing these two would be amazingly useful across software industry. Okay, any questions about like the high level goal or questions or problem that we're addressing here? All right. Okay, so one way, I mean, this seems like a lofty goal, but let's try and be more precise about it. What does it mean to say two programs are kind of computing the same function? And can I formulate this in an even more general setting? Okay. So we will do so by this really elegant definition called semantic properties. Okay. So unlike syntax, you know, syntax is like, you know, whatever you're writing your code in, you know, what variables you use, you know, whether you have semicolons or something like that. Semantics is supposed to be about what is the program computing, right? And semantic properties are those which exactly do that, which is they only depend on the input-output behavior of your program. Okay, let me first state it just informally, and then we'll define it formally as well. So we will say, you know, property of a program, like, you know, whether the program does what you want it to, is it equivalent to something else, you know, or some other properties. If it only depends on the input output behavior or functionality of the program. Okay. So I, give you a program and I ask you, does it have some property? And we'll call the property semantic if it only depends on the input output behavior of the program. It doesn't depend on seemingly irrelevant things like, okay, does the program have a variable named foo? Does it have a variable named blah on it? Does it have 100 lines or 200 lines? Does it have, some character, or not? Okay. So all of those would not be semantic properties, right? Because they are not talking about the input output behavior, but about the exact implementation that you are using. Okay. But how can I mathematically state this condition that the property only depends on the input output behavior and not on the exact implementation of the program? Any suggestions? So how can I define it formally? How can I specify it formally?
You could say like for all x, like program A of x is equal to B of x.
Right, but we are talking one step out, right? So if two programs are kind of have the same input output behavior, we want to say that they have this property or don't have this property. Okay, so we'll do exactly that. But again, this is all about reasoning about programs. Okay, and as I said, a big part of computer science, we'll take computer security, take programming languages, and software verification, and many of these things, they deal with reasoning about programs. Okay, so their inputs are programs. And we are talking about one of the most important questions in all of these fields. So we will say a function whose inputs are bit strings, again, which are interpreted as programs or Turing machines. Okay, is semantic if it satisfies the following thing. First, we'll say two programs, we say m comma m prime, two programs, Turing machines, are equivalent if for all x, m of x equals m prime of x. Okay, so two programs are equivalent. It's kind of national definition. If the input output behavior is exactly the same on all inputs, for every x, whatever m is doing, the output is exactly the same as what m prime did. Okay, and we will say a function on programs f is semantic if for all equivalent programs m comma m prime, f of m equals f of m prime. Say a property of programs is semantic if we wanted to say the semantic if it only depends on the input output behavior. And the way we are formalizing it is to say take any two programs, if they're equivalent, either they'll both satisfy the property f or they both won't satisfy the property. Okay, any questions about the definition? I think it's a kind of a very nice way to formalize this notion that the property only depends on the input output behavior. Any questions? Yeah. Okay, let's look at some examples, right? So my first claim is halt on 0 is a semantic function.
Yeah, I agree with that.
Okay, so we'll get there. But maybe it's not true for halt on 0, but there could be other seemingly simpler semantic functions. Okay, so let me give another example, right? Let's say the function I'm interested in is majority. Okay, which is majority of m plus 1 if m is equivalent to majority function, 0 else. Okay, remember, it doesn't exactly matter how we define the majority function, but we have this majority program, right? We took an input string and checked if the input string had at least as many ones as zeros, right? Is majority is something that just checks, give you a source code, is it exactly computing the majority function or not? Okay, this is kind of hitting this bullseye on whether I want to check if my program meets the functionality that I want. If I can do this for is multiplied, then I'm able to check, you give me some input, I can check in an automated way whether it's exactly computing the multiplication algorithm. Okay. So is majority is also a semantic function. Okay? Because it doesn't depend on what's the source code of m. It only depends on what is it actually doing on specific inputs and outputs. Okay, yeah.
So to clarify, our function f is like just a function that it's kind of like a predicate that determines whether a given input program has a semantic property.
Has some property or not. And then we're saying, okay, that is the property semantic. If the property is semantic, if it's kind of only depends on the input output behavior as formulated here. Okay. Actually, to better illustrate, what this definition is doing, let me give some non-examples. Right? So let's say I define a new function f, which does the following. It takes a description of a machine and checks is 1 if the description ends with a 1 and 0 else. Is this a semantic property? Any guesses? It's taking a program, checks if it ends with 1 or not. Yeah. Exactly. It's about the implementation, right? And if I ask you the question, okay, does this program have the variable foo? That's not a semantic property. I can have the same implementation by changing the variable name without changing anything about the input output behavior. Right? So f here is not semantic. Okay. And I can also give other examples like this. One, if m halts in 100 steps and 0 else. Okay. 100 steps. I can even make it more specific. 1, 0. Okay, so it's saying, does the machine halt within 100 steps when given 0 as input? Then it's satisfying this property. Otherwise, it doesn't satisfy this property. Okay. And is this a semantic property? No, right? Because again, I can get the same input output behavior, but not, with different outcomes for f. What if I just have a trivial loop at the beginning of the program which runs for 100 steps? The input output behavior is not changing, but the outcome of this function f would change. Okay, so f is not semantic. Okay, and here's another somewhat trickier non-example. And maybe so recall the toddler function, right? So when we define toddler function, it was okay, you take the toddler of a machine as its description, and then you check it's 1 if m halts with 0 as first bit and 0 else. Okay, so this was the toddler function. Given any input machine m, description, it checks whether the machine, when given itself an input, halts with 0 as the first bit of the output, and otherwise it outputs 0. Okay. So is toddler a semantic function? If not, why? If yes, why? Any guesses? Like, is toddler semantic or not? So the thing to keep in mind is that semantic means it should really only depend on the input-output behavior of the machine, right? So my claim, toddler is not semantic. Okay, why? If I have two machines, m and m prime, both are equivalent, that doesn't necessarily imply, does not necessarily imply that toddler has the same behavior on both of them. Okay. If it were semantic, then given any two equivalent programs, the output of the function should be the same, but there's nothing in the definition which guarantees that these two are the same. Okay. Yeah. Exactly, right? Because the definition of toddler really talks about running m on the description of m, right? So on the when I ask for toddler of m, it's going to check what is m doing on the description of m. If you ask toddler and m prime, it's going to say, okay, what is m prime doing on the description of m prime? Okay. So toddler, by definition, it looks at the source code of the program that you're inputting. Okay. Whereas other things like halt on 0 doesn't really talk about the source code. It talks about the input output behavior. Okay. So like, this depends on m of m, depends on m prime of m prime. Okay. And we don't have any way to compare these two. The equivalence only tells you that m and m prime give the same output on the same input. But here, it's talking about two different inputs. The descriptions are different. Okay. As a thumb rule, if your property is looking at the source code, like does the source code have a variable name, something, then it's not semantic. Okay, and by and large, in most applications in security, programming languages, and so on, you're predominantly interested in semantic properties. Okay. Any questions about the definition of semantic? Okay. Okay, so Rice proved that every non-trivial semantic property is uncomputable. Okay, it's kind of like a treasure trove of uncomputability results. Like we saw, okay, Halton zero is uncomputable, not empty is uncomputable, but now Rice's theorem says you pick any semantic property as long as it's non-trivial, meaning, okay, there is one really silly semantic property, which is the constant one function. Okay, that's a semantic property because it's the same for all machines. In particular, it's the same for equivalent machines. And there's also another silly semantic property, which is the constant zero function. Okay, except for these two, all semantic functions are uncomputable. Okay, there's just no saving grace. Any semantic function you can imagine is uncomputable except for these two. Yeah.
So why not all of them?
So that's an excellent question. So again, so eval is not really a function, right? Because sometimes it tells you whether or not something is running into a loop. It doesn't tell you whether or not something is running into a loop. It doesn't halt on all inputs, right? It has 0, 1, and this perpendicular symbol, which was our shorthand for saying, okay, the program has run into a loop. Okay, whereas when we're talking about the semantic things, it's about specific outputs, 0 or 1. Okay, so that's the reason why. Okay, so there's just no saving grace in terms of semantic properties. As long as you are not the constant function, it becomes uncomputable. Okay, if this were not the case, then of course, all of these areas would be very happy. We would have like a nice theory for many of these things. But because this is so hard, there's a lot of work to do within them, and we'll address some of these challenges and ways to get around this in the next lecture. Okay, but let's take a 5-minute break, and when we come back, we'll see the proof of this theorem, and then we'll take it from there. Okay, so let's try and prove this, and we will prove this by a reduction from Halton zero. So the proof is not complicated, but you have to kind of twist, you have to think about things in a non-trivial way. It's not very long, but you have to kind of think in a meta way as we've been doing always. So what do we really want to show, right? So suppose you have f is a non-trivial semantic property. It can be any non-trivial semantic property. For instance, it could be, okay, is my program equivalent to majority? Is my program equivalent to parity? All of those things. Okay. And we want to show that under this case, f is uncomputable. And we will show this from a reduction. So let's kind of set up some understanding of how to use this. So what does non-trivial mean? We have to use both of these things, right? Otherwise we won't be able to prove it. So what does non-trivial mean? It means that there exists some machine M0 and there exists some machine M1 such that f of M0 is 0 . Okay. So basically it's saying, you know, you have your space of all programs, all Turing machines, right? And here's F is kind of saying, okay, this machine is a 0, this machine is a 1, and so on, right? It's non-trivial means it's not a constant function. So there is some machine on which some input which makes F output 0, and some input which makes F output 1. Okay. So that's that we are getting from non-triviality. And now the proof is kind of clever in the following sense. You know, we have to use some ingenuity here, and we're going to look at the following program. So idea, get a reduction. Okay, so I'm going to define a special program. It's going to be a silly program, but bear with me. It's called the infinity program. So what does it do? You know, actually, you know, I don't even have to do anything. It's just a program which goes in an infinite loop. Okay, I'm just writing this a equals 0 as a placeholder, right? A program that goes in an infinite loop. Okay, so a Turing machine that does not halt. Pick any Turing machine that does not halt on any input. You know, you give it some input, it completely ignores that input and just goes into a loop. Okay, so it does not halt on any input. Okay, and now we need a bit of a case analysis. All right, so case 1. So there are two cases, right? You know, what does F do on this function? One case is the semantic property F classifies this as 0 for whatever reason. It could also say 1, it could say 0, it doesn't matter. Okay, let's do one case and then we'll go on to the other case. So now we are going to say that in this case, so under these assumptions, right, you know, F is non-trivial, semantic property, and F of inf equals 0. In this case, we can reduce halt on 0 to F. Okay. What does this mean? So that is, we need a reduction such that for any Turing machine M, halt on 0 of M should equal F of R of M. Okay, this seems kind of very hairy, right? We don't know much about F. I don't even know what F is, but I'm telling you, you can come up with this reduction. How? Well, all we really need are these three things. that there is some m0, so that f of m0 is 0, there's some m1, and then this guy. Okay, can you give me some suggestions on how we might be able to come up with such a thing? How can I come up with this reduction? Right, so we need to come up with some R of m such that this equality holds for all machines. So one suggestion, let me give a hint, is ideal. Suppose m is a machine that does not halt on 0. Then we want f of R of m to be 0, right? It has to equal, it has to be identical. The behavior should be, we want f of R of m, the reduction should also output 0, right? So then I'm going to say R of m should be equivalent to inf. On the other hand, if m halts on 0, then halt on 0 of m would be 1. The output would be 1, right? But for the equality to hold, we need f of R of m to be 1. But the only thing we really know about the semantic property is that there is some function, there is some program. It could in fact only be a single program for which this holds, right? So we need this thing to hold. So I want a reduction. I want a way to transform my input program m into two things in such a way that whenever m halts on 0, what I get is a program that goes into an infinite loop. If it does not halt on 0, its behavior is exactly that of m1. How can I do that? Any ideas? Okay, so let's see. So this is what we are hoping to do. Okay, when I write, let me now describe the reduction to do this. So R of m is actually going to be the following program. Right, so it's def n of some input z, and what it does is run actually, let me use x here. Almost, I think you're almost right. R can be universal Turing machine. We just want it to be something to exploit this non-triviality, right? We want to make sure that these two things hold. Okay, so let me now, this is the reduction that we're going to use. There are many other options to come up with, but this is one reduction, one way to do it. So it's just kind of two lines, right? Reduction, remember, is a way to transform one input to another input. So here I'm taking the input for alt on 0, and I'm defining a new program, which I'm going to view as input to my semantic property, capital F. And let's check the cases. So what do we need to show? So this is the what right? So I define the reduction, and how part R is computable, right? So we are not running these eval functions. We are just kind of copying those instructions. We're just changing the text. So it is computable just as it was for when we were doing the reductions earlier. So, but why? Okay, so we need to now analyze why, right? So what does why mean? So if halt on 0 of m equals 1. So we need to show that this equality holds, right? You know, the behavior of halt on 0 and f are identical. So suppose m actually halted on 1. What can you tell me about R of m? What is its behavior like? So if m halted on 0, then you would terminate in this step and go to the second step, right? So what does this tell me about the program R of m? What's, you know, its behavior is equivalent to m1. Implies R of m is equivalent to m1. Okay. Any questions about this? So basically, we just have one line here, right? You know, whenever you halt on 0, you go to the next step. So I'm just running m1. Okay. Which in turn implies that f of R of m. Remember, f is semantic. Yeah, we should be returning m1 comma x. Oh, yeah. Yeah, that's exactly what I write. Maybe you mean I should be saying return here? Is that the question? Oh, yeah, we should be returning. That's what I meant by when I said that. Yeah, exactly. Right? So f is semantic, right? So its behavior, f of R of m should equal f of m1, which we know is 1. Okay? And on the other hand, if halt on 0 of m equals 0, then what happens? Meaning m does not halt on 0. What is R of m equivalent to? So this new reduction program that we built is equivalent in behavior exactly to it's equivalent to inf, right? You know, inf is a program which goes into an infinite loop every time, right? And when halt on 0 of m equals 0, this program R of m also goes into infinite loop every time. You know, it never gets to this second step at all. Okay. So okay. So therefore, we have the desired equality, right? There is a way to translate an input for m to an input for f so that you have the equality. Okay. So thus we have a reduction from halt on 0 to f implies f is uncomputable. Okay, so if we could solve f, we could solve halt on 0, but we cannot solve halt on 0, so we should not be able to solve f. Okay, so that's kind of the whole proof. Like it's a little sort of mind bending, but basically what you're trying to do is kind of exploit this dichotomy, right? I give you a program M and I ask you to check whether M halts on 0. Now I spit out a new program which has two behaviors. Like, when M halts on 0, its behavior is identical to M1. When it does not halt, you just get an infinite loop. Okay, and this is all happening in this case. And there's one more, we assume that f of inf is 0. Okay, and I can say we have to also handle the case where f of inf equals 1. Right? And it is not too difficult here. In this case, you can get a reduction from not halt on 0, but I'll leave that as an exercise from the homework. So let me say the idea is reduction from okay, so you can kind of do the same thing. We just have to slightly change things, but nothing materially changes. Okay, any questions about this? So in summary, we have this very powerful theorem. So Rice's theorem is extremely powerful, as I said, because you can use it to now get like an infinite number of uncomputable problems, right? Any non-trivial semantic property is uncomputable. Okay, so it's just you can get all kinds of uncomputable functions, right? So for example, there is no automated way to do software verification, right? Rice's theorem just completely kills it. If I give you any program and I ask you to check, is it computing majority? There is no automated way to do it. Because I can just build up like this dummy simple trick, right? It's not even that complicated, and make you solve halting problem. If someone comes and says, okay, this function is actually going to compute parity, that's good, but there's no way to verify it. There's a question, is there a way to prove that a function is semantic? Yeah, so you have to prove it mathematically. Like, you can basically show that it only depends on the input output behavior. Meaning whenever, and it's also very formal, right? Equivalence is formally defined, which is, if I have m and m prime such that m of x equals m prime of x for all x, then f of m should equal f of m prime. And that's a formal definition. So you can actually verify it always. Okay. So uncomputable. All right. Any other questions? And one should keep in mind that, this gives you dozens, I mean, as I said, many uncomputable problems, kind of really kills the hope for meta reasoning about programs. Any property that you care about, it just cannot be solved on a computer. Any property you care about programs cannot be answered by a program. Okay. So let's take a 5-minute break. And when we come back, we'll see why this theorem is such a buzzkill and ways to get around it. Okay. All right, let's take a 5-minute break and we'll resume at 1 o'clock. Okay. So let's summarize our discussion of Turing machines, right? We started this about 2 weeks ago. So we started by defining this new model of Turing machines by extending the notion of DFAs in 2 natural ways, right? We said, okay, DFAs were limited to make only a single pass on the data. So let's allow it multiple pass. And then we also said, let's allow it memory, long memory. Okay, that was the notion of a tape, and that led to the definition of Turing machines. And we saw examples that they could do things which are not possible by DFAs. And I stated without proof, this theorem that Turing machines can actually simulate Python programs. We didn't prove it, but that is true. And this is a theorem that we can actually show formally. And then we went many steps ahead and formulated this hypothesis, that something that we think is true about nature, about the universe that we live in, is that Turing machines are really the model of computing, in the sense that anything that is possible to be solvable by a physical computational device is possible to be solved by a Turing machine. Like, for instance, Turing machines can simulate quantum computers, whatever they are, and all kinds of other crazy computational models. They are simulatable by Turing machines, at least anything that we have so far. That's the church-turing thesis. And then we also had this notion of universality, right? And again, this was a formal thing that we proved, saying that there is a single Turing machine which can simulate any other Turing machine, right? You can view a Turing machine as the description of the machine as input to this other machine, and we can solve it. And finally, we also use this interpretation of code as data, viewing the input to the machine as a machine itself led to all kinds of weird circular things. In particular, it led to our first uncomputable problem, the toddler problem. And starting from toddler, we built this web of reductions, right? We started with toddler is uncomputable. And from there, we went to halt is uncomputable. And from there, we went to halt on 0 being uncomputable, to not empty. And finally, we also had Rice's theorem. Right? All semantic properties, all non-trivial semantic properties are uncomputable. Okay? So there is like a good and bad side to Turing machines. Right? They are very powerful. You can do all kinds of things that we care about on Turing machines. You can multiply, add, write programs in it for any task that we think is possible. But on the other hand, this great power comes with great restrictions on reasoning about programs. If your model of computation is very powerful, then your ability to solve questions about those programs on computers is limited. Okay. So in some sense, we also talked about this notion of Turing completeness. Right? You can try and come up with restricted languages, models of computation, but more often than not, things become more often than not, they become Turing complete. I mean, people have built Turing complete models based on something out of Super Mario games. Okay, so you can build all these programming languages which are all Turing complete, which in some cases can actually be a feature, right? I want a powerful model of computation, which is great. But also sometimes it can actually be a bug, right? A feature. Can use it to program anything. Why could it be a bug? Well, I can't program anything, and more importantly, a bug because reasoning about programs becomes unsolvable. Okay, and this is a real world scenario. It's not just like a huge, some thing that we care about in theory. This bug can be devastating in practice. So for instance, there's this whole story about Ethereum, the cryptocurrency. So they had an instrument to do some kind of contracts, digital contracts, which they call DOA, digital contract market. Okay, so they wanted to build this whole new market based on cryptocurrencies and based on blockchain technology to be able to do contracts online in a decentralized way. And at the height, this whole thing was running on Ethereum. You allocated Ethereum coins for it, and it was worth $150 million. Okay, and as part of it, they actually introduced a new language to build these contracts, and they said, it's kind of sound, we cannot do weird things in it, but some hacker, or you might call that person a wise investor, or some person who actually took a CS 181 course in their life, figured out that this language actually is Turing complete. So they found a contract that loops forever. And they used it to basically transfer $60 million into their own fund. Okay, so they found this bug basically, which kind of a subcontract, which was making the whole contract system loop forever. And as a result, they were able to siphon off $60 million, which is a huge money, and also like a huge chunk of the market DOA. And then there was this whole split about Ethereum, the whole currency split into two segments, there's Ethereum Classic and Ethereum, the new Ethereum, and so on and so forth. So a lot of debate on whether or not they should have done it, and they should have just given this person that much money, but that's another story. Okay. So the punchline here is that Turing completeness can both be a bug and a feature. Sometimes, I want to actually design a programming language for which asking these meta questions, checking whether or not the program could cause me to go into an infinite loop on some input is decidable. I want to prevent people from uploading programs on my server, which will make them run forever. How can I do that? One way to say is that, okay, you are not allowed to use for and while loops at all. And maybe you avoid all kinds of go-to statements and all kinds of things like that. Maybe then you can avoid it, but then are you limiting the power too much? Okay. So this motivates the question of studying restricted computational models. So I want to design restricted computational models, things which are going to be more limited in power than Turing machines, but useful for some specific purposes. And I can still answer at least some of the meta questions that we care about, right? And this is a perspective we are going to take towards one very important class of models, for which we can answer some of these meta questions and also are important by themselves. And